Hello guys. Today we are going to discuss quiz 1. So first let's double check that the sound is okay. So you can indicate it somewhere. Yes. Right. So you can see that I've posted on Slack that we are going to use this latest thread for your questions. So I need to say that we are going to discuss specifically quiz 1. So please leave your questions about assignments, about Kaggle to the following threads. So it's a pretty new format. We used to have only assignments, so the quiz is intended for you to read articles, and I guess we'll have some nice discussions. So maybe some arguments. Yeah, of course, this format, inverted classroom, is ideal for live meetings, so like offline in real life. So where you discuss, write formulas on a desk and so on. So this YouTube format is not ideal probably for that. But still I'm going to go through all the 10 questions in our quiz. I'm going to motivate maybe the solution that we stick to. Or maybe I can admit that some questions are completely unsuccessful. It can be the case as well. And if you have some really serious objections, then please post to the dedicated Slack thread, to this one. And otherwise use YouTube chat to chat to each other, to discuss questions. So I'll try to read this Slack thread. Okay, so let's start. So the first quiz was dedicated to decision trees and random forests. And we started as in topic 3 with a general question about the basics of machine learning. And the first question was about main ML tasks like classification, regression, and clustering. And you needed to select the one option which cannot be attributed to either classification, regression, or clustering. So here I've provided 4 options, and yeah, we had pretty much actually a lot of discussions there in the thread. Sorry, I don't think I can see YouTube chat here. Maybe one of you can confirm in this Slack thread that the sound is okay and that we can go on. Let's pause here for a bit. And actually whether the screen is also all right, because I see some blinking on my own computer. Maybe you can justify that it's all right. Okay, sound is okay. Yeah, nice. Let's go on. All right. So here, right in the first question, you see that grading-wise, we'll change it a bit. It can happen. Here I need to say that quizzes are less formal, maybe less strictly graded than assignments. So in assignments, we think that, yeah, there are, at least we hope that there's a single option which is 100% correct, and the assignments are strictly graded. Kaggle competition is the simplest option. You just either beat baseline or not, so it's really simple to grade. Here we'll have some discussion, and indeed, even in the first question, we'll make some modifications. Okay, so the first option, identifying a topic of a live chat with a customer. So I suppose that it's going to be classification, but indeed, this is not mentioned in the text. So it depends on whether we have a labeled dataset or not. So actually, this is my task at work right now. So we are in telecom operator, and we've got a lot of customers talking to us, reporting all the different things. It's a huge data mining challenge to extract some meaningful insights from there. And the first thing to do is actually to classify chats into billing, or some questions about service, or maybe the guy wants to churn, so it will be contract end. So yeah, of course, for this purpose you need a labeled dataset, and when you actually got it, then it turns into a multi-class classification. But indeed, you can argue that if we don't have a labeled dataset, then we would apply clustering or something unsupervised like topic modeling. So this is indeed questionable. Okay, nice start. Actually, the first option in the first question is not 100% correct. So I've marked the latest option as correct, but this one can also be treated as as clustering might be. The second one is for sure it's grouping news into topics. It's just a systematic case of clustering. So it's even formulated as one of the examples of clustering. Predicting LTVs, lifetime value of a customer, so the amount of money spent by a customer in a certain large period of time. The amount of money spent, the formulation means that it's regression. Yeah, so we're going to predict some numeric variable. So then, definitely for this we need a labeled dataset, and we suppose we've got it. So we've got some history about our customers. We can measure how much time they spend. Again, it's one of my former projects. Here, of course you cannot do it in an unsupervised manner, so it's a clear case of regression. And then the final one, listing top products that a user is prone to buy based on user click history. So this is a ranking task. Yep. How ranking is different from classification, regression, or clustering? So first of all, we also need a labeled dataset, so it's a supervised learning setting. And ranking is somewhere in between classification and regression. So you actually for each entry you need to rank some of possible options. Actually, it can be solved via classification setting. So even if you just apply logistic regression and you output probabilities. Okay, so far we've covered trees and boosting. Yeah, with random forest or boosting, you can also output predicted probability, and you can actually rank your options according to this predicted probability. Yeah, so if your instance in a labeled set is a pair of user and some document, indeed you can sort by predicted probability. But by definition, this setting is the type of ranking. Here at this point we see that we don't cover ranking in our course, so we encourage you to read, to think, to ask clarifying questions in the dedicated thread. But indeed this final option is of type ranking. Okay, but due to these arguments about the first option, as for grading, so we'll be treating the first or the fourth or both of them as a correct option. So we'll modify grading here a bit. Okay, I'll check your questions in the thread and then we'll move on. I suppose that we had a really nice discussion in this thread about quiz 1. So of course we cannot repeat a lot, so like discussing all the possible nitty-gritty details of all 4 options in this case. We can have some follow-up discussion. I guess next time in quiz 2 and 3, I'll be answering your questions myself, because it will be easier for me then to conduct this live session. Will the notebook with solution be shared after the live stream? Yes, for sure. So the format of this live session means that we discuss all the topics. Maybe we argue somewhere. Maybe somebody will be pissed off a bit. It's okay. But the idea is that we discuss all the points, and I actually come up with some grading. And after that. After editing a bit this notebook, of course, it will be shared. Fourth option is an example of recommendation engines, right? Can it be solved using clustering as well? Yeah, so it's a clear-cut case for recommendation system. So in general, it's a ranking problem, but indeed, a particular case is a recommendation engine. Maybe you can try to solve it unsupervised, so without labeling, but I doubt so. Yeah, maybe there are some works in academia about unsupervised ranking. Nothing from top of my mind. But for sure, you won't be able to do it really well without a labeled dataset. So a recommendation system ranking, like including search engines, so typically these tasks require a lot of data. Yeah, I also used to solve this task, maybe in the end, during live session -1, I can quickly recap my experience in these tasks as well. Okay, so let's go on. In question 2, we actually have some math. So now we are going to discuss all this, some hard skills of data scientists. Here, let's first read the question. So maximal possible entropy is achieved when all states are equally probable. Try to prove it yourself for a system of 2 states with probabilities p and 1 minus p. And then what's the maximal possible entropy of a system with n states? And so all logarithms are with base 2. Okay, so here are 4 options. The easiest way to solve this task was just to plug in n equal 2 into all these formulas and see that, yeah, the third option would be correct. So, yeah, I would say this is a smart solution. It doesn't require you to do a lot of math. It's just, selecting the most suitable option. Let's see what I mean here. Yeah, we'll see how well I'm going to draw a formula here, but yeah, we'll try. Okay, so we've got entropy, this formula that we've covered in articles, in the assignment. So this is the formula for entropy of a system with n states. And in our case, in case of classification, we consider, so for each class, we've got a predicted probability of instance being attributed to this class. So in case of n equal to 2, this will be minus p log 2 logarithm of p, and then let's plug in the probability for another class. It will be 1 minus p, so minus 1 minus p logarithm of 1 minus p. Okay, so how can we actually get the last option? Just plugging in n equal 2. Yeah. So in case of 2 classes, I just clearly stated in the question itself that maximal possible entropy is achieved when all states are equally probable. So we'll be analyzing this function that we've written here a bit later. But if we know that entropy is maximal, as stated in the question itself, the maximal is attained when P1 predicted probability for class 1 when it equals to predicted probability to class for class 2, and it's obviously equal 1/2, then entropy will be maximal. So it actually corresponds to P equaling 1/2 in this formula. So if you carefully plug it in, so for 2 states, maximal entropy will be minus 1/2 logarithm of 1/2, and this is the second term will be just equal to this one, so it multiplied by 2. We get minus logarithm of 1/2. So actually, this is how we get 1. So if you just compare it with the provided options, so if n equals 2, then we get actually the third option. Right? So for n, which is equal to 2, we've got logarithm of 2, and it's actually 1. So it's an easy way to hack this question, for sure. But let's actually analyze this formula. So let's first prove that the maximal possible entropy is achieved when probabilities are equal. So we'll start with this simpler case when we've got only 2 possible states. So basically, we need to maximize this function that we've already written here. Yeah. So this is the expression for entropy of a system with 2 states. So P is the predicted probability that a system is in the first state. So 1 minus P is the probability for the second state. And so here, obviously, we just need to maximize this by P. So here we've got a basic calculus task. So let's just set the derivative to 0 and see whether we indeed get that the optimal solution would be P equal to 1/2. Deleted everything. It was not intended. All right, never mind. So we've got this expression minus P log P. Yeah, I would implicitly mean that all logarithms are based with 2. In case of natural logarithm, I will be writing ln. All right. So now I'll go through these derivations. This might be a bit boring for you if you are familiar with calculus, but I will quickly go through it. So probably it will be easy for everyone to understand. So yeah, as we stated in prerequisites, yeah, we ask for you to be able to take simple derivatives like we are going to do right now. In case you know it really well, just wait a bit. We'll go through this derivation. Okay, so first of all, we need to find extrema of this function. So if we calculate the derivative of this function with respect to P, and set it to 0, then we'll find some P star, which is going to be an extremum, right? Either minimum or either local minimum or local maximum. Let's do this first, and then we'll actually discuss what we need to do else to actually find the global maximum of this function. Okay, so first of all, we need to find the derivative of entropy with respect to pi. So here we've got one subfunction p multiplied by another subfunction. So we need to take derivative of that. So it's a derivative of a complex function. So we first take derivative of p, which is basically 1, multiplied by this function log p. Okay, so here I'll be using a simple rule. The derivative of function u multiplied by function v is u prime times v plus u times v prime. So it's one of the basic rules to take derivatives. Okay, so we'll have minus log p. I took derivative of p, and then minus p times the derivative of this logarithm, which is actually 1 over p, but our logarithm is based with base 2, so we've got natural logarithm of 2 in the denominator as well. So the derivative of log log t x will be 1 over x, as in case of a natural logarithm, but then we'll have here natural logarithm of t. Okay, so far I've taken derivative of the first term, and pretty similar things with the second term, but we need to be careful with signs, right? Minuses and pluses. Okay, so again, derivative of the first multiplier will be -1, logarithm of 1 minus p, and finally minus 1 minus p, and derivative of this logarithm, which is going to be 1 over 1 minus p, again natural logarithm of 2, and a derivative of a complex function, so we also need to multiply by -1, which appears from this expression. All right, so if we simplify it a bit, what we have here, let's see, we can simplify here, here, and here. So we get minus log p plus log 1 minus p, and then we've got -1 over logarithm of 2, and plus this term, so sorry, we just don't need to write it. Oops. Okay, so that's the expression. Yeah, because in the end we simplified this term with this term. All right, so now this is the expression for the derivative, and now let's set it to 0. So if we just explicitly set it to 0, it's not a good practice to write just like that. So let's stop here. So we found an expression for the derivative of this function. So now we are setting it to 0, and we'll find this p star, this extremum, right? So I'm going to delete what I've written so far. Let's just remember log 1 minus p minus log p. And it's good to double check whether I did it all right. Yeah, so this part in the lecture. Okay, so probably I missed 1 over logarithm of 2, but it's a constant term. Indeed, let's take a look whether I need it. 1 over logarithm. No, I think I don't need it here. Okay, anyway, it's just a constant. So we've got this expression, and now let's set this derivative to 0. Right, so we had this expression, log 1 minus p minus log p. Now we put a star here, we set it to 0, so this will be our extrema. So, and we can mark it here that now p is equal to this p star. So some value of the probability of p, which will drive this expression to its extremum. Okay, so this is solved really easy. So if logarithms are equal, then these expressions are equal. So this left part is equal to this right part. We've got 1 minus p star is equal to p star. And then finally p star is equal to 1/2. All right, so this is going to be an extremum. How do we know if it's a maximum or minimum? We need to analyze the second derivative, right? So just a quick recap here. So geometric meaning of a derivative is actually whether the function is growing locally or not. So if we've got some function, so at some point, at some specific point, let it be f of x, and we've got x. At some point, x0, I need to make a disclaimer that yeah, I'm going to describe things not really strictly. So as a data scientist, I code worse than a programmer, and I know mathematics worse than a mathematician. I'm going to describe the essentials behind all this analysis, but it's not 100% strict. Yeah, so I'm not going to provide a clear definition of a derivative, but the meaning. So the intuition behind the derivative is actually the growth of function at this point x0. Yeah, so we can clearly see that the function grows here, and the sign of the derivative here is positive. Yep. So f prime at this point f prime at the point x0 is greater than 0. Okay, so the second derivative is, by the same token, it's how the first derivative actually changes. And the idea behind the second derivative is whether the function is convex or concave. So let's consider such a function, a parabola, and let's think about its derivative. Yeah, so we see that here the function is growing, so the derivative is positive, and that gradually, if we move to the right, we see that the function starts to grow slower and slower. Yeah, so the speed at which the first derivative is being changed, that's the second derivative. So here we see that the growth slows down. At some point it's actually 0, and then the function starts to decrease. Then the first derivative is negative. So the decreasing first derivative is actually the same as the second derivative being less than 0. And on the contrary, if the second derivative is positive, then a function is convex. So here the second derivative is positive, and we started from a pretty steep decreasing. Then the first derivative was getting higher, higher, and higher, and then at some point, actually, the first derivative turned into positive, so the function started growing, and then faster and faster and faster. That means that the second derivative is greater than 0. Okay, so to cut a long story short, we to prove that this p star equals 1/2, to prove that it's going to attain maximum to entropy, we need to analyze the second derivative, and we actually need to show that the second case holds, that the second derivative is negative. That's why it would mean that we'll have a clear maximum here. Alright, so we analyze the second derivative, so we need to take a derivative of this expression. Yep. So second derivative of this function with respect to pi would be, we need to take derivative of a logarithm. We've got 1 minus from here, and minus 1 over pi, and it's all multiplied by 1 over natural logarithm of 2. Alright, so we'll skip this term, it's just a constant, we are not interested in that, and so we'll say that it leads to what? 1 minus p over 1, 1 over p minus 1, minus 1 over p, right? And so what do we get from here? So we've got, so here we need to multiply by p, here by p minus 1. And so we've got in numerator we'll have just 1. In denominator we'll have p and p minus 1. All right, so let's analyze this expression. So this one, it's going to be on our second derivative. And we can see that as long as p is greater than 0 and less than 1, which is obviously the case, so p as a probability is in this region from 0 to 1. So this expression is actually strictly negative. I'm skipping a pretty hard case, so when p is equal to 0 or 1. So these are border cases which shall be handled specifically. But otherwise, if actually p is not 0 and not 1 precisely, then everything is all right with the second derivative. And as far as we've got this p minus 1 here, we see that the second derivative is negative. That means that entropy as a function is concave, yeah, so like in the second picture, and that's why our extremum is actually a global maximum. Okay, let's pause here for a while. I'll take a look at your questions. Of course, this involves some of calculus, which might look annoying for some of you. I also had to recap a lot for the second part, a bit more complex. For some of you it might be really very easy to follow. Maybe you are a bit bored even. But let's see. Okay, looks like this derivation was pretty much clear for you. Okay, let's move to the second case. I'll leave it optional because, yeah, your mathematical background differs pretty much. I will only say that if we need to maximize this function in a general case, when we have n states, we'll have a constraint optimization problem. Yeah, so we will need to maximize this expression, but we will have a constraint that all probabilities are going to sum up to 1. So let's first ignore it and get we're not going to get a true solution here, so we'll make a small mistake, but this will lead to generalization when we actually need to resort to Lagrange multipliers. Yep. So the first idea for you to maximize this function, so now we'll have n states, and we've got the same thing, which we want to maximize. How things are going to differ in the case of n variables. Basically, we need to derive these partial derivatives of entropy with respect to each of pi j. So let's take some index j, and we need to calculate the derivative with respect to this variable. So with you see that there are no multiplication terms where several probabilities are involved. So this sum is pretty simple to differentiate. Yeah. So if we take a look at some variable pi j, then we'll only have the term minus pi j log 2 pi j, and so the derivative will be precisely the same as we got in the previous case. Yeah. So it will be minus log 2 pi j minus pi j 1 over pi j logarithm of 2. So this will be just minus log 2 pi j minus 1 over logarithm of 2. Okay, and so this will hold for all j's, yeah, for j from 1 to n. Okay, so we also need to analyze the second derivative, which in this case is going to be a Hessian, so a matrix of all second derivatives. You need to show that it's negatively semi-definite. Actually, it also boils down to analyzing second partial derivatives. So second partial derivative of s with respect to pi j is going to be really simple. So it's going to be, let's see, so taking the second derivative, just minus 1 over pi j, and again a constant term logarithm of 2. So again, it's strictly negative. So this derivation looks pretty simple, but there's only one caveat why this is not a right derivation. So no, for sure what I've written so far is true. But if we want to find extremum, let's see what we get if we just set this expression to 0. Yeah. So if we just solve this equation to find extrema, we'll actually find. Okay, I'll write it in red because it's not correct. So if we set it to 0, we'll find that pi j star is going to be equal. Okay, let's start with its logarithm. So its logarithm is equal to minus 1 over logarithm of 2. So if we solve it, it's going to be pi j some expression e to the minus 1 over logarithm of 2. It can be simplified a bit, but you see that this is not a correct correct solution. Yeah. So if you can simplify it and calculate, and it's going to be something like okay, don't remember, but let's say something like 0.4. And you might suspect that no, this is not a correct solution because we didn't account for a constraint that all probabilities shall sum up to 1. So basically the solution will be pretty similar to this one. We still need to differentiate and analyze the second derivative. But actually, a maximization problem with such constraint is solved with Lagrange multipliers. So those of you who are interested can go through this proof, can read about it. I've inserted some links. So the whole idea is the same, and you'll come up with an intuitive solution that maximum is attained when all probabilities are equal, and they are equal to to 1 over n. And if we plug in this expression 1 over n, we'll get finally this formula log n for maximal possible entropy. Okay. So I'll leave it to you to actually dive into this derivation. So of course I will share this notebook. And at this point, when we plunged, when we actually delved into some math, I need to say that if you are really intimidated, if it looks like a dark random forest for you, don't be discouraged. So you can go on with the course just with its practical part. We'll have some more quizzes, some more math in next module with linear models. Might be that yeah, some of the math will be even a bit more involved, but it's not something crucial. Yeah. So actually, yeah, it's fun to understand this entropy, to derive these all these mathematical expressions, to analyze entropy, but it's not actually crucial for practice. Yeah. So you can go on with Kaggle, with other assignments. So this is just a nice add-on, yeah, to understand this theoretical part. So just you can just skip what I've been describing here for quite a while, for this half an hour probably, and you can go on with the course for sure. All right, so more questions? Okay, so let's go on. not so quick. Just one suggestion, maybe next time the notebook with solution will be published before live session, so we can see if everything's clear before watching. All right. The idea is that I'm going to edit it, and I will share the final version with you, which might be a bit different. But anyway, yeah, I see that you would like to follow what I'm explaining here. Okay, as a temporarily version, which might differ a bit. Anyway, I'll share it in this thread. So precisely the same notebook that I'm showing right now. All right, so sorry, yeah, that's a common problem. When I write on the bottom right of the screen, my own image covers what I'm writing. That's true. Yeah, indeed, I need to be careful about it. I guess at this point, my face really irritates you a lot. Perfectly understand. All right. Let's move on to the third question. It's much simpler, so it involves the very same code and the very same simple formulas that we had in the article. So we had a toy example with 20 balls. So some 11 of them were, let's quickly count. Yeah, some 11 of them were yellow and 9 of them were blue. And we analyzed how actually information gain works. So if we were to split yellow and blue balls, which splitting criterion we would select? Yeah, in the article we analyzed that splitting at this point with criteria x is less or equal to 12. So this is going to yield the highest information gain. And the question in this quiz is which information gain, which value of IG will actually have if we split by condition x is less or equal to 8. Okay, so here you can do it by hand, of course, but I've written simple code which calculates entropy, so the very same formula which we've been analyzing in the previous question. So we just need to iterate over all probabilities, and entropy will be minus the sum of these terms, p numpy log 2 of p. Okay, so a little bit controversial point here was that lots of you assumed that entropy of initial state is 1. But I've made a statement about it in the mlcourse.ai news channel that no, we are going to calculate it precisely. So that's why we need to calculate the entropy of initial state. So we just plug in here probabilities of 9/20, a probability that that a random ball is going to be blue, and 11/20 that it's going to be yellow. So we plug in initial entropy. Then if we split by this criterion that x is less or equal to 5, in the left group we end up with 4 blue balls and 5 yellow balls. So we calculate entropy in the left group, and then we also calculate entropy in the right group. Yeah, so maybe these shall be better refactored as S left and S right. And then if we perform this computations, left and right. Okay, so finally we've got this value for information gain. If we round it, we actually get the fourth option. Okay, I think this is pretty straightforward. Only that, indeed, if you assume that initial entropy is precisely 1, then you would have end up with the second option. But there was a discussion about that. So yeah, I also had to make a clear statement about this, yeah, basically to pass the quiz successfully, you need to chat on Slack, you need to analyze what's written there. So that's also some part of, yeah, a bit of communication here. Okay, the fourth task, the fourth question was pretty much controversial. So yeah, you can already see that grading-wise, you all will have full credits for this. This is indeed important to understand which arguments influence actually decision tree, the way it builds decision surface. At this point, yeah, I can analyze your answers, so your responses. I said I was going to stick to heuristics, so if a lot of you miss some question, then there's a problem with question formulation. So it's for sure it's the case with question 7 and 8. So even Google Form itself warns me that these are frequently missed questions. So for question 4, yeah, I guess a bit more than one half actually made precisely that choice that I meant. So it's less than these 63%, which I sort of settled as a threshold, but it's not strict, of course. Okay, let's analyze what I meant here. What actually was I supposed that you analyze to actually answer this correctly. Here I am. Okay. So in a toy binary classification task, we've got D features, but the target depends on the first 2 features, and all other ones are noisy. So if we were to fit a decision tree classifier, what arguments we are obliged to set correctly, then otherwise we just cannot fit this function. Okay, let me show what I mean by that. Okay, so we've got an ellipsoid. Well, in 2-dimensional case, it's just an ellipse. Yeah, you could have used Wolfram Alpha or Matplotlib to actually plot this function. But this equation actually stands for an ellipse. So we've got 2 variables here, x1 and x2, and we've got some sorry, how is it called? Never mind. Okay, so we've got some region which is defined by this equation: x1 squared over 4 plus x2 squared over 9 is less than or equal to 16. Right? Right. Okay, so if these are x's x1 and x2, then this defines a region. Yeah, so if we plot it as with green, then this will be this inner part of an ellipsoid. Actually, this point will be 2 and this will be 3. So maybe I depicted it not precisely, but you get the idea. Okay, so our target actually depends on this condition. Y is actually equal to this indicator function, whether this holds. So we'll have a binary classification task. So in this green region, we actually have y equal to 1. I'll depict it by pluses. So we will have some points here, some pluses here, and minuses outside this elliptic region. All right, so the question is actually about fitting a decision tree, and there was some hint by Roman Gerbert, so our teaching assistant for this quiz. So there was a clear hint by him that think of decision tree arguments which, if set incorrectly, would just hurt fitting this function. Okay, let's analyze that. So decision tree is going to build a decision surface where each part of this decision surface is parallel to one of the axes. So it's one of the basic things that, it's stated in the article, and it's one of the things to understand about decision trees. So if we were to fit a decision tree, so it's going to build some decision surface which looks like a ladder. Yeah, so it will look something like that. Okay, I'm not going to draw it symmetric, but you get the idea. Okay, so let's analyze argument max. It's easier to start with max depth. So what if we set max depth incorrectly? So suppose it's equal to 1. Then basically it means fail, that we fail to actually to learn this decision function in the right way. Yeah, so if max depth is equal to 1, then it's trivially something like that. Yeah, decision surface just fails to get this idea of this underlying function y. Okay, so I will rewrite it like that. So if max depth is equal to 1, then we fail to learn this function. That means that max depth needs to be set correctly, and you can have an idea that max depth shall be large enough for decision tree to learn this function. So the same holds with min samples leaf. So the second argument, min samples leaf. Actually, it plays pretty much the same role, but a bit different. So it's very close to 1 over max depth. If min samples leaf is large enough, this will regularize the tree very much. So let's say we've got L instances in our dataset. So if we set min samples leaf to be equal to the worst trivial case, if it's equal to L, yellow is not a good color here. Okay, sell it. If it's equal to L, then again fail. Yeah. So what would it mean? It means that we were not growing with a tree if there are less than L instances in each leaf. Yeah. I guess even if we set it to be 1/2, well, rounded probably, then still it would require that that we need to have almost 1/2 of the whole data set in one of the leaves. So here we'll fail to learn this function as well. So again, it will end up with some decision function either as trivial as in a previous case, or maybe we'll have 2 more splits, so a decision function might look something like that. So we will fail. We'll fail to learn this decision function y. Again, if we set max features incorrectly, same story. Yeah. So next, let's analyze max features. Max features is actually the number of features that we use to learn this decision tree. Yeah, suppose we just set it to 1, then again fail. So if we only use 1 feature to make a split, then we also fail to learn this function y. Let's try to depict this decision function. So we'll be using only 1 feature to perform splits. So yeah, we will be doing something. Let's suppose it's only feature x2. So then we are able to only make splits which are parallel to x2, perpendicular, right, to axis x2. And so again, we are not going to learn this function. So finally, for criterion, we can, of course, speculate that if we set criterion to be MSE for regression, then we fail to learn it. But then, well, sklearn would not allow you to use criterion, regression criterion in a classification task. So basically, we end up with criterion either Gini or entropy, and actually they work pretty much the same. So there is no clear argument why we are going to fail if we use Gini criterion or information gain. So criterion is the only one argument which is left here, which is not going to influence the build decision function that much, right? Okay, so what I meant is that max features, min sample sleeve, and max depth are going to be correct answers. But as I said, yeah, you all will get full credits for these questions. Some of you might argue, wow, I've spent so much time digging into this question and now you are giving full credits to everybody. But remember, the final goal is to learn something. So if you spent a lot of time analyzing these decision surfaces, how each argument influences this surface, then it's good for you, yeah? So then you've gained something. Okay. More remarks here. Since you are so generous with scoring, can I please get the credit for answering exactly the opposite question in quiz 1, marking the options 1, 2, 3? Okay. No. But setting max features to anything greater or equal to 2 will fit the tree well. So in essence, the max features is irrelevant in this example unless it's set to 1 or 0 extreme cases. Yes, indeed, that's why this question is not ideal. So that's why it introduced some confusion. So what it's stated in the question itself, which parameters have crucial effects on accuracy? Crucial meaning that if these parameters are set incorrectly, then accuracy can drop significantly. Okay, so indeed, I didn't state clearly here that we need to analyze any possible value of these arguments. Indeed, if we set max features to 0 and 1, this will hurt. But otherwise, max features, yeah, doesn't. So if max features is set to large enough value, then indeed it wouldn't influence that much. So if x1 and x2, these crucial features, are covered, then decision tree is going to pick them to build a decision function, indeed. Okay, so number 5. This is a practical question. So you're asked to load the iris dataset, then train a decision tree with max depth of 4, fixed in random state for reproducibility. And then how many pure leaves we've got here. And by pure leaves, we mean where all instances are attributed to one of the classes. So we'll have Gini equal to 0 in these cases. Okay, so I'm not commenting the code, so it's very simple and it's actually taken from the article. So we load the iris data. We've got x, 150 instances with 4 features, and we've got a vector of y. We fit a decision tree classifier, and then we plot the tree. Okay, I'll comment it a bit. In one of the latest versions of sklearn, we've got this plot tree function, so we'll use it here. Yeah, so basically we can plot this tree, and now we need to analyze leaves. A small caveat here is that we've got yes, 6 leaves in the bottom line, but we actually we've got 8 leaves in total. Yeah, so we've got one more leaf here and one more leaf right here on the second level. Okay, so and quickly going through all the leaves, we can see that 7 of them are pure, so all instances are attributed to one of the classes, and only one of the leaves is not pure. So the answer is 7 here. And I also plot a decision tree in an old fashion. I just found that we get better resolution if we don't use this plot tree function. But maybe I didn't tweak this plot tree function long enough. So yeah, if we plot the tree a bit differently, we get a better picture with higher resolution. Okay, let's move on. Question 6 is covered in the article, so I think you didn't have problems with questions 5 and 6. Okay, 5, 72% correct answers. Number 6, 87. Yeah, actually we can skip question 6 because it's purely covered in the article. We just only need to substitute values with different ones provided here. Okay, so somewhere here in the article, we've got this example. Shall I find precisely where it is? Yeah, you can find an analytic expression for this theorem in a Jupyter notebook accompanying this article. Okay, so this one, topic 5, part 1. Okay, so it's all analyzed here, and you only need to plug in different values for this question. Yep. Okay. On the contrary, question 7 is the most controversial. Okay, for 7 and 8, you'll get full credits. But let's quickly discuss what I meant there. But indeed, the questions are not really successful because, yeah, only a bit more than 1/3 of correct answers in question 7, and question 8 is just 50-50. Okay, this can happen. I perfectly allow these for quizzes, not for assignments, but for quizzes. Still, the goal is to discuss something and to actually understand the material better. Okay, so if we go back to topic 5, part 2, there is an example of decision surfaces built by a decision tree and random forest. And we see that yeah, for decision tree, the boundary is a bit jagged and jerked, and yeah, we've got these all these strange part of decision surface. So the question was to actually analyze how decision tree is different from an ensemble, from bagging or from random forest, and so why actually this happens. All right, so what I actually meant with this correct answer is that decision tree can be sensitive to outliers. Actually, a decision tree can be easily overfitted to any dataset, so we can pretty quickly build a decision tree with each leaf being pure, so with all instances in the leaf belonging to one class. Okay, so let's draw some toy example. Let's say that again our classes are ideally separated with a circle, and we'll have pluses here, minuses here, and maybe we will have some outliers, some pluses here in the negative region. So if we actually fit a pretty deep decision tree, it will actually, yeah, probably it will try to learn this function, this circle, but then it can overfit to some outliers, yeah, if it's long enough. So basically, that's why we need to to regularize a decision tree, right? So in order for tree not to be influenced that much with outliers, we actually restrict its depth or min sample sleeve, and so on. So that's why we'll actually have these parts. How would I describe them? Okay, these peaks, as we see in this picture, right? So basically, this would mean that for a single training instance, a decision tree has created a couple more conditions. Yep. So if we go back here, if we have features, so x1 and x2, basically this part of a decision surface, this part, which is created specifically for this outlier, actually these are three more conditions, right? So to fit to this outlier, we created three more conditions. So somewhere in our tree we got x1 is less than or equal to, sorry, x2, first x2 is less than or equal to some value a here. Then we had a separate condition, x1 is less than or equal to some value b, which I plot here, so this threshold. And then somewhere again we've got x2 less than or equal to c. So you see that we've got three conditions just for one training instance. So that's what we precisely call, informally called by overfitting. So three more conditions just for one instance. Okay, so that's why I actually marked this option as correct. Some of classification rules built by a decision tree can be applied only to a small number of training instances. So that's why we actually have these this jagged region of decision surface. The problem with this question, my failure is that other options might be true as well. So that's why this confusion here. Okay, so the first option is that ensembles ignore some of the features and thus picking only important ones, they build a smoother decision boundary. Well, I tried to make some other options which are not correct but look plausible, and basically I've overdone that. Yeah, so indeed introduced too much confusion. So yeah, first of all, ensembles don't ignore, generally they don't ignore features. So though each tree in an ensemble or each basic model in an ensemble, it can be fitted, so it's actually fit to a subsample of features, but then in general ensembles don't ignore features. Yep. So they try to use all of the features and pick up those which are actually important. Of course, we can set arguments, so these hyperparameters, we can set them in a way that the ensembles would ignore some features. So let's suppose we've got 1,000,000 of features and we set max features to, not max features, but with this bagging fraction. If we set it to just 1%, then, yeah, and if we fit just 5 trees, let's say, then of course we'll ignore most of these 1,000,000 features. But in general, this is not true. In general, ensembles don't ignore some of the features. But as for this argument that if we pick only important ones, they build a smoother decision function, okay, I don't have a good enough objection why this is false. Yeah, so indeed, let's think about it. Indeed, in the very same case, let's go back to this ellipsoid that we had in the previous task. So our decision function depended only on x1 and x2. Sorry. Okay, so we had a target only dependent on 2 features, but we also had, so in general we had D features, and so most of them were noise. Indeed, if the algorithm is distracted by some of noisy irrelevant features, then probably it would overfit and build this jagged decision function. And indeed, ensembles can actually pick up these two important features, and that's why they are going to build a smoother decision function. So the first option might also be true. Yeah. The idea behind this question was to actually analyze these two pictures and explain why we see this difference. So that's why probably the first option was not meant here as an explanation. But I have to admit that it can be true as well in other cases. Yep. Probably the fact that the question is tailored to precisely this picture, maybe it was not mentioned well enough. All right, as for the last case, when fitting a decision tree, if two potential splits are equally good in terms of information criterion, then a random split is chosen. This leads to some randomness in building a decision tree, therefore its decision boundary is so jagged. Again, everything up to this point, so that's actually true. So due to some randomness in building a decision tree, indeed, its decision boundary can be random, unstable, I would say. So refitting a decision tree with a bit different random state can result in a completely different boundary. Probably it's not an explanation for precisely this difference. Yeah. Though a decision tree is unstable, probably this argument wouldn't explain the difference that we see with ensembles, right? Okay, so a decision surface is unstable. Yeah, due to this randomness, so we can end up with a bit different picture with a bit different these peaks. Oh, how would you call this? Okay, so these spikes. Yep. So maybe indeed, due to this randomness, these spikes can be a bit different. But it's not the best explanation why in the second case, in case of ensembles, we don't see these spikes. Okay, so at least here I motivated why I selected the second option as a correct one. But again, we sort of disqualify this question. Let me see some of your possible objections. Okay, so probably I skipped some of the questions for the previous one. In the max features parameter description, there is a note stating that the search for a split does not stop until at least one valid partition of the node samples is found, even if it's required to effectively inspect more than max features. Would you explain what it stands for? What is a criteria for valid partition? I guess it's from documentation to random forest. The search for a split does not stop until at least one valid partition of the node samples is found, even if it requires to efficiently inspect more than max features. Okay, yeah, humble here a bit to analyze that. I'll answer it later. But it sort of says that yeah, we explore different features. So in random forest, at each step, we explore this number of features. Let's say 10, if max feature is set to 10, and we are looking for good splits. So what? Yeah, indeed, what they mean by valid partition here. I guess the idea is that if we fail to make a split with some set of features, then we would look for another one. Okay, I don't have a good explanation right now, so we'll do it later. There's currently some issues with YouTube chat. It's not working for Yorko. I'm answering questions on Slack, so I'm not answering your questions in YouTube chat. So please, as stated on Slack, please use it for communication between each other. I found Wolfram Alpha useful for questions like question 6. Yes, Wolfram Alpha is a perfect tool. I really regret that I didn't know about it when I was a student, so I really spent a shitload of time actually deriving expressions by hand. That was a bit monotonous and stupid to waste time like that. if I knew Wolfram Alpha at that point, I would have been more, my learning would have been more efficient for sure. Okay, so then question 8. Again, the results are 50-50, and it's mostly due to the language. Yeah. The random forest learns a coefficient for each input feature, which shows how much this feature influences the target feature. Is it true or false? Well, basically, that's true for linear models, so we're going to cover linear models next time. The key word here is learns. By learning, we mean adapting model parameters to actually fit the target variable. So of course there's a huge confusion with feature importances here, but basically feature importances is a good side subroutine which helps you to interpret random forest, but random forest basically doesn't learn feature importances. Yeah, so of course it's a very subtle argument, and it's mostly about mostly about language, mostly about formulation of this question. So yeah, by learning in this setting, we would mean the case of linear models, when we actually learn a coefficient for each feature, and then our target variable precisely depends on these parameters that we actually found during optimization. In case of random forests, yeah, these feature importances that we found, we cannot say that they directly influence the target feature. But again, obviously the formulation is vague, so let's move on. Suppose we feed random forest regressor to predict age of a customer. It's actually a real task. It's good to understand the age of the customer. And the maximal age seen in the dataset is 98 years. Is it possible that at some point we'll predict for some customer his age to be 105 years? No, this is a notorious statement that random forest and trees and boosting, they cannot extrapolate. So if we take a look how we actually make predictions in leaves, it would suffice to take just a decision tree. We see that we're not going to predict some value which is larger than anything seen in our dataset. If we have a simplest case regression, if we were to learn some function like that, and we build a decision tree, how it's gonna look like? We'll have some parts of this decision surface, and then we'll have these jumps. So these dashed lines are not actually part of our surface. Actually the decision function will be these horizontal pieces, right? So actually a decision tree will be checking some criterions. So if it's the only variable x, then we'll be at any point we'll be comparing x to some threshold. Let's call it tau, and we'll have some tau 1, tau 2, tau 3, so all these different thresholds, and in each node we'll be checking whether x is less or equal than some tau. And in the end, so let's consider some leaf. In some leaf, we'll actually have a set of our observations. If we were to draw them here, so our real observations from the training set, depict them with green. So maybe the underlying function is this black one, but our observations are a bit noisy, so we'll have some green points probably somewhere close, so around this black underlying function. So these greens are basically our data observations. And for some leaf, we'll actually have a bunch of values. Let's take a look at these leaf with these 3 observations, green ones. And so probably we have some specific values here.
just approximately, maybe somewhere here we've got 10, and these 3 observations would be 11, 12, and 9. Then actually we, as a prediction for this leaf, we'll just take the average. So if we have the next instance which passes through this decision tree and we end up in this leaf, then the prediction for this leaf will be just the average of these 3 points, yep, of these 3 values. So actually here we'll, in this leaf, we'll predict 20, 32, so 32 over 3. So it's 10 and 6 period. Okay, so as long as we predict the average value of all the instances in a leaf, then obviously we can never predict something higher than the maximal value that we encounter in the dataset. So somewhere in one of the leaves, we'll actually have the largest value encountered in the dataset, and still we're not going to predict something larger than that. So if somewhere here we've got a maximal possible value in that we've seen in our dataset, let's say 13. So somewhere in one of the leaves we'll have this value, this 13, and still in the very same leaf we are going to make a prediction which is less or equal to this value 13. So we are never going to predict something larger. And question number 10, select all statements supporting advantages of random forest over decision trees. Some of the statements might be true, but they don't support these pros, these advantages of random forest. So you're not asked to select just true statements. You need to select those which underline pros of random forest. Okay, no problems with question 9, and yeah, basically no problems with question 10 as well. Let's go through all these statements. Random forest is easier to train in terms of computational resources. No, of course, random forest is much harder to train as compared to a single decision tree, because random forest consists of multiple trees. Of course, we can speculate that random forest can consist of one tree. Yeah, but we're not covering these these particular cases here. Yeah, maybe. Okay, I didn't make this trivial remark that in random forest we consider that we think that random forest consists of some large number of trees, not trivially one tree. Okay, so obviously random forest is harder to train as compared to a decision tree. Second point, random forest typically requires more RAM than a decision tree, than a single decision tree. This is true, but it doesn't underline random forest advantage. As compared to a single decision tree, this is a disadvantage. So of course, consuming more RAM in general, it's a disadvantage. Random forest typically achieves better metrics in classification and regression tasks. That's true. So that's why random forest is so much popular. Indeed, typically switching from a decision tree to a random forest would result in some 5, 7, 10% increased accuracy. Yeah, there was a question whether pure, just single decision trees are ever used in production. Yeah, I would say when random forests were not that popular, they used decision trees in credit scoring tasks, maybe in churn as well. As far as I know right now, it's only in medicine, in medical tasks, they use single decision trees, and they are a bit more involved. They've got some significant tests in nodes, so these are some specific types of trees. But in general, of course, random forest works on average much better than a single decision tree. Single decision trees prediction can be much easier interpreted. That's true, but it underlines pros of a decision tree, but not those of a random forest. So it's good that a decision tree can be easier interpreted, and indeed it's a disadvantage of a random forest that it's much harder to interpret than a single decision tree. Okay, I'll check whether you've got more objections, more comments. Yuri, personally, I don't think that you should be so generous with scores. If most people answered the question incorrectly, well, that means the question was hard and people did not dedicate enough time to dive into it. In my opinion, all questions are constructed well enough to be answered correctly. Okay, it's your opinion, which is respected, of course. Yeah, I guess some 20% of all the students who coped with the assignment might think that, yeah, questions are all right. I personally think that the only failed question is question number 7. But still, I think, yeah, we're here to learn stuff. So I think why not being generous with points in this sense? So as long as there is some confusion with the statement, which is justified statistically, yeah. So if we see that many people didn't cope with the question, like question number 8, then I would think, yeah, why not just disqualifying this question? In the end, we discussed it, you discussed it in the thread, so the final goal of learning something while discussing the question is actually achieved. Okay. Can you please explain how random forest actually calculate feature importances? If they're not learned, what are they? Okay, we had a contribution from one of the guys with a nick creepy neighbor. So the topic 5 part 3 is almost entirely rewritten. So Mikolai contributed a part of material precisely on that. So how actually sklearn's random forest feature importance work? What's the idea behind permutation importance in general? So with some toy examples and so on. So then a toy example with a single sklearn's decision tree. So it's pretty well covered here. I have to admit that I probably need to reread it once again when I have free time. But feel free to analyze it and to report some inconsistencies via GitHub issues. But this question is pretty well answered in this topic 5, part 3. Yeah, I see some questions about Kaggle, about assignment 2. No, sorry, so it's been 1 hour and a half so far. So we've got this time actually for quiz 1. So there's pretty much to discuss here. And I'm afraid quiz 2 will be much more controversial, much harder, because the theory behind linear models it's actually vital. It's good for you to understand it, and it's a bit more involved. All right, so I guess we've covered most of the things. I'll still answer some of the questions in the Slack thread. All right, so thanks for joining today. And I guess this was useful. So I hope that you actually read all these topics, because in previous sessions we were more focused on Kaggle competitions and assignments, and basically it was really easy to ignore most of the course material, most of these articles. But here we actually force you to read and to understand all this material. So I guess that was helpful. And one small announcement that we will move deadlines for quiz 2 and quiz 3. So right now I've designed it's I've I've given some 8 days for you for these quizzes. For linear models, for these quizzes, definitely not enough. So we'll move these deadlines closer to the corresponding deadlines to assignments. So I'll write about it in mlcourse.ai news. It means that you'll have 3 deadlines in a row. Like on Friday, you'll have a deadline for a quiz. Then on Saturday, we'll have this live session. Then on Sunday, you'll have a deadline for your assignment. Don't complain. So obviously, I've given you more time for quizzes, so it's good for you. And the fact that you'll have these deadlines grouped, clustered together, it only means that you need to do some time management. So yeah, wish you good luck with assignment 2. And if all the theory in this quiz was too hard for you, just don't drop out the course only because of that. Go on with practical part. Okay, good luck.